In this video, I'm going to explain some details about Transport Layer Security, or TLS. It's what you use when you use HTTPS, Secure HTTP. TLS is specified in RFC 5246. Transport Layer Security is exactly that. It provides security at the transport layer, so between applications. It's a session layer on top of TCP. It provides a stream abstraction just like TCP. So to most applications, it looks just like TCP, a bidirectional, reliable byte stream. But TLS adds confidentiality, integrity, and authenticity to the stream. So, using TLS properly, you can protect your communication from eavesdropping, tampering, and spoofing attacks. The most recent version of TLS is version 1.2, specified in RFC 5246. TLS started as the Secure Socket Layer, SSL, by Netscape, back when the web was just starting. The version order is SSL 2.0, SSL 3.0, TLS 1.0, TLS 1.1, and now TLS 1.2. TLS is used by HTTPS. So what ciphers and keys does TLS use? It has a wide range that are available. As part of setting up a TLS session, the client and server negotiate 4 separate ciphers. The first is the cipher used to authenticate the server. You can also optionally authenticate a client. The second is the cipher used to exchange symmetric keys. The third is the cipher used for symmetric confidentiality, and the fourth is the cipher used for symmetric integrity. These are negotiated in the 5-step session initiation protocol. This all happens after we open a TCP connection. So these messages are sent over TCP. So we have an open TCP connection. In the first step, which is sent as clear text, the client sends a list of ciphers it supports and a random number it has generated. The server responds with what ciphers to use, its own random number, and a certificate containing its public key. This is also sent as clear text. In the third step, the client sends something called a pre-master secret to the server, encrypted with the server's public key. Using this pre-master secret and the 2 random numbers exchanged in the clear text, the client and server compute the keys for the session. I'll explain the details of how this works in a moment. But for now, realize that at this point, the client and server have generated the symmetric keys that their ciphers need. Next, the client sends a finish message, encrypted and macked with the symmetric keys generated with the server random, client random, and pre-master secret. This message includes a MAC of the handshake messages to ensure that both sides saw the same messages. The MAC is also computed the symmetric key generated from the server random, client random, and pre-master secret. Finally, the server sends a finish message. This is secured similarly to the client finish message and also contains a MAC of the handshake messages. Macking the handshake messages allows TLS to protect against an adversary trying to force the 2 parties to choose a different cipher. Since the first 2 steps are not secured, they have neither confidentiality nor integrity, then an adversary could perform a man-in-the-middle attack to try and change the offered and selected ciphers. Macking the handshake messages lets them detect this. So now, at this point, we have a secure connection protected through symmetric ciphers that both sides have agreed on. So what does that look like? Well, to provide integrity, TLS needs to break application data up into chunks that it can provide message authentication codes for. So TLS takes the application stream of data and breaks it up into records. There are also records that don't contain data, such as records that generate new keys. But let's focus on data records. TLS takes the application stream and breaks it into data records, which state their length and have a MAC. These records are encrypted with the chosen ciphers and keys and then sent over TCP. This appears as a stream of data to TCP, which then breaks it into segments. Records can be much larger than TCP segments, so a single record might be broken into many segments, and record and segment boundaries might not line up. TLS includes compression as one of its features. If, for example, you configure TLS to provide integrity but not confidentiality, then you'd be sending plain text. English text are generally very compressible, almost 10 to 1, so you can configure TLS to compress the data. By default, compression is off. If there's confidentiality, then compression will help since the bits should seem like they're random. So let's look at how TLS establishes its session keys. Remember, both the server and the client provide random numbers. That way, if even one of them has a bad random number generator, you'll still have randomness. The client also sends a pre-master secret encrypted with the server's public key. The client and server both combine these three pieces of information to create something called a master secret from which they generate their session keys. Once they compute the master secret, the client and server throw away the pre-master secret. They generate 6 keys, whose lengths are determined by the ciphers used. They generate a key used to encrypt data from the client to the server, a key to MAC data from the client to the server, a key to encrypt data from the server to the client, a key to MAC data from the server to the client, a client initialization vector for ciphers that need it, and a server initialization vector for ciphers that need it. Having this master secret, the client and server can regenerate new keys by choosing new random numbers. So you can resume a session with the same master secret, but with new keys. Here's a picture of the whole process. The client and server take this client random, server random, and the pre-master secret and pass them as input to something called the pseudo-random function, or PRF, which basically generates bits that look random. This produces 48 bytes worth of random bits, the master secret. TLS takes the master secret and the 2 random values and passes them as input to a pseudo-random function to generate as many bits as you need for all of the keys. So for example, if the MAC keys are 512 bits and the write keys are 256 bits and the initialization vectors are 128 bits, then you call the pseudo-random function enough times to generate 1,792 bits, which become the keys.